You probably remember learning about gas laws in school, right? That neat, simple formula. Well, what if I told you that formula has let's call it a dark side? That under the wrong conditions, trusting it could be seriously dangerous. Today, we're going to dive into the secret life of gases, when the ideal just isn't real. I want you to imagine something. Let's say your job is to handle high-pressure gas cylinders, and the number one rule is don't let them explode. You pull out the formula everyone learns in science class. But what if that trusty formula lies to you? What if it tells you everything's fine when it's actually about to blow? Yeah, this is where our story gets very real, very fast. So the culprit at the heart of this whole thing is something called the ideal gas law. And don't get me wrong, it's elegant, it's simple, and most of the time it's super useful. The problem is, it's all built on a myth, the myth of a perfect gas. So what even is this so-called ideal gas? Well, think of it like a physicist's fantasy. It's a gas made of particles that are just points in space. They take up zero room, and they completely ignore each other. No pushing, no pulling, nothing. It's a perfect model, because the math becomes ridiculously easy. But as we're about to find out, easy and right are definitely not the same thing. Okay, so this whole ideal model hinges on two big assumptions. And both of them are totally wrong in the real world. First, it pretends that molecules are like little ghost particles. They've got mass, but they take up zero space. And second, it assumes they're completely antisocial, just flying right past each other without even a hint of attraction. These two little simplifications, they're about to cause a huge problem.
So when do these perfect assumptions really fall apart? Well, they fail when things get intense, specifically under high pressure. Let's look at a pretty high-stakes example where this perfect myth creates a very, very real problem.
All right, here's the scenario. We've got a 4-liter cylinder, and it's packed with 500 grams of chlorine gas. Now, this cylinder is built to withstand pressure up to 40 atmospheres. That's 40 times the air pressure around you right now. But when we plug all these numbers into our standard ideal gas law, it spits out a pressure of 43.1 atmospheres. According to our perfect formula, this cylinder isn't just full, it's a ticking time bomb.
Whoa, okay, so why did the ideal law give us such a terrifying results? To figure that out, we have to peel back those perfect assumptions and look at how real gas molecules actually behave in the wild.
And here's the disconnect, plain and simple. In reality, molecules are not ghosts. They have actual measurable volume. And they're not antisocial. They actually have a slight attraction to each other, especially when they get crowded together. These two simple facts are exactly why the ideal law fails us when it matters most. Let's break down that first flaw. When you shove a ton of gas into a tiny space, the molecules get seriously crowded, and all of a sudden, the little bit of space each one takes up is no longer so little. It's kind of like a subway car, right? At 3 in the morning, the car feels huge, but at rush hour, the volume taken up by all the people becomes a very, very significant factor. This crowding effect changes the pressure in a way the ideal law just completely misses. Now for the second flaw. It's all about attraction. When molecules are squeezed close together, they exert a tiny pull on one another. So imagine a molecule is about to slam into the container wall. Right before it hits, it gets a little tug backward from its buddies. That little tug means it doesn't hit the wall quite as hard, which, when you add it all up, reduces the overall pressure on the container. So, our simple, beautiful equation is broken. But don't worry, thankfully, a Dutch physicist named Johannes van der Waals figured out exactly how to fix it. Van der Waals looked at the ideal gas law and said, okay, this is a good start, but we need to get real. His new equation didn't treat gases like some perfect theoretical idea. Instead, it tackled the two big flaws head-on, the actual size of molecules and the forces between them. This work was so important, so foundational, it ended up winning him a Nobel Prize. And his fix was just beautiful. It's so logical. First, his equation tweaks the volume. It says, hey, the container isn't totally empty. The molecules themselves are taking up some room, so let's subtract that. Then it tweaks the pressure, saying, wait, the molecules are pulling on each other, which made our pressure reading too low. Let's add that lost force back in. It's a direct correction for reality. And just look at the difference this makes. When we recalculate our chlorine cylinder problem using the van der Waals equation, we get a pressure of 28.2 atmospheres. That is a 15-atmosphere difference. But more importantly, it's way, way below the 40-atmosphere breaking point. The cylinder isn't a time bomb at all. It's perfectly safe. The more realistic equation gave us the true answer. Now, this deep dive into real gases doesn't just keep things from exploding, it also explains something the ideal gas law can't even begin to touch: how a gas turns into a liquid.
This process, liquefaction, it's what happens when you cool down gas molecules so much that their own attractive forces, the ones the ideal law just ignores, finally win the battle. The molecules just don't have the energy to fly apart anymore, so they clump together and become a liquid.
So why should you care? Well, think about this number. When you take natural gas and turn it into a liquid, liquefied natural gas, or LNG, it takes up only 1/600th of the space it did as a gas. 1/600th. That completely changes the game for how we store and transport energy around the world.
And the impact is just massive. These ultra-cold or cryogenic liquids have totally revolutionized entire industries. We're talking everything from shipping fuel across oceans and performing delicate cryosurgery in hospitals to preserving biological samples and even separating the very oxygen and nitrogen from the air we breathe.
But the behavior of real gases doesn't just matter in a lab or in a giant shipping tanker. These exact same principles are at work on a planetary scale, shaping our atmosphere and our weather every single day. You know how the air gets thinner the higher you climb a mountain? Well, this is why. That predictable drop in pressure as you go up, what scientists call hydrostatic balance, it's a direct result of gravity pulling on real gas molecules that have real mass. It's why airplanes need pressurized cabins and why climbing Mount Everest is such an incredible challenge. And if you want to see this on a truly grand scale, look no further than our weather. The incredibly complex dance between pressure, temperature, and volume in our atmosphere, which is really just a giant container of real gases, is what creates everything from a nice, gentle breeze to a colossal spinning hurricane. So we started with a simple, ideal formula and found out that, well, it was dangerously incomplete. The big takeaway here is that scientific models are incredibly powerful tools, but we always have to remember their limits, especially when the stakes are high. The reality of gases turned out to be more complex, sure, but also way more interesting, explaining everything from industrial safety to the weather. And that leaves us with one final thought. If the model for something this fundamental was a simplification, what other ideal models might be shaping our view of the world, just waiting for a more realistic perspective to unlock a much deeper truth?